All right, so let's go ahead and take a look at conjectures and counterexamples. I'm going to real quickly just go through this first part with the reasoning because we're not going to get too involved with that. Your reasoning is basically, your brain, you got the wheels in your head turning, okay? You're drawing conclusions, facts you already know, logical, okay? You've got two different kinds of reasoning. The first one's going to be inductive reasoning. I'm going to jump straight to the second bullet point here because we've got a lot of words and stuff in the first one that could confuse you. The reasoning, this is the reasoning that you will use when you are trying to make a decision. And this decision is based on what you've already seen. Make sure you pause to get the rest of that written down, okay? The reasoning that you will, this reasoning you will also use to draw a conclusion. And it's based on patterns, sequences, or series. And we'll be seeing that a little bit later. You gotta make sure you pause and get it all written down. Your deductive reasoning, this reasoning is going to be based on facts, rules, or definitions. It is based on things that have already been proven, shown, or verified. So this is like me saying, I'm using deductive reasoning when I tell you that a triangle has three sides, because that's a fact. There's no change in that. There's no ifs, ands, or buts. It's also part of the definition. Okay? But again, we don't get too abrasive with the reasoning here. What we do need to make sure that we are understanding is conjecture. Okay? Your conjecture, right here, let's go ahead and highlight conjecture because it's part of the title. Obviously, it's going to be important here. A conjecture is just this educated guess. So we have an educated guess based on known information. So you know something and you're like, well, you're giving me this information. Well, based on what I know, this is my conjecture, my educated guess. Okay? It is a result of inductive reasoning. We don't need to focus too much on that last point. Okay? And then we get to see that making a conjecture involves looking at a pattern, sequence, series, design on what you think will come next, and stating it. Okay? So we'll go ahead and take a look at what conjectures involve. So when you're making a conjecture, your conjecture can involve extending a pattern or sequence to the next term. So here we can put extending. Or drawing a picture to visually represent data. And we'll see that happen in here. So in example one, we're focusing on that. We're going to be doing a lot of just extending that first bullet point, extending the pattern. So we take a look at A. We see this pattern 7, 14, 21, 28. We want to know that next item or that next term. We should be able to see that it's going to be 35. So when I was teaching the classes, I had some good conjectures. Majority of these conjectures were adding 7 each time, or increasing by 7, or something of that sort, jumping by 7. You're using different words, but you're meaning the exact same thing. Okay, so here we'll just put add 7 each time. So that's your conjecture. You're looking at this pattern. You're saying, okay, what's my educated guess? What do I see going on? You're adding 7 each time. I also had a student that I was really, really happy to hear. In this situation, it works. He said that each term is the next multiple of 7. And I was like, wow, that's a really, really good conjecture there. Now, it doesn't always work that way. If I started with 1 and added 7 each time and go 1, 8, 15, it wouldn't work that way. But in this, that is another conjecture you can you can conclude from this exact pattern here. So the next one, we're going to talk about the conjecture first. First thing I want to do is make sure that we understand that in angles, because with the conjecture that we're going to come up with is every single word is going to be a math word, okay? What we need to notice is we have 3 heptagons here, 7-sided figures. Each one has a point on a vertex. And by the way, I mean vertex, if I cover up all this and we just look at where this point is, that's an angle. The point is in the vertex of the angle. So polygons are going to have vertices, plural for vertex. Okay? And I know we can all see what's going on here. Each one, and again, I've gotten several things today. It's skipping a vertex. It's going 2 vertices each time. So again, we're saying different things but meaning the exact same thing. But what we're going to do, and I've also heard students were saying it was rotating. I had a student in one of my classes who almost said it verbatim. I had to ask, "Do you have a copy of my notes?" Because he was almost verbatim what we're going to be writing down. He told us that it was moving clockwise 2 vertices, and that's exactly what's going on here. So we're going to write point rotates. We'll put 2 vertices clockwise. And so, like I said, every single word, point, it's a math word. Rotates, math word. 2, obviously a math word. Vertices, a math word. Clockwise is a math word we use with our rotations. So here comes the fun part. Let's draw the next term. So mine were getting worse and worse throughout the day, and I think I finally figured it out. Okay, I'm going to start off and I'm going to draw this top little portion, the top 2 sides. Okay, and then I'm going to go to the other side and I'm going to draw the base, and I'm just going to connect 2 lines going from there. And this is not art class, okay? So it doesn't matter if it doesn't look good. The whole point here is we need to make sure that on the last term, that point was in the bottom left vertex. So we're going to have to go start at the bottom left vertex and either, what some students say, skip a vertex or move 2 vertices. And this will be our next term or our next item. The next pattern, I heard some amazing things today that it almost knocked me on the floor. I just did not expect answers that I got today. We're going to keep it simple and sweet what's happening between each one of these numbers. And in fact, one class was giving me all these great examples of conjectures and never gave me the most simple conjecture of all we're doing is we're adding a 0 between the decimal and 4 each time. So here we'll put add a 0 between the decimal and 4. What else I was hearing was, my first class, where the first student who gave me a conjecture on this one said, well, we went from the tenths to the hundredths to the thousands. I was like, wow, using our math words. Another one I really, really liked was that we were dividing by 10. When you divide a number by 10, you're moving that decimal to the left one. So every time you divide by 10, you move that decimal over to the left. And so there's another thing I was hearing was you're moving the decimal to the left one more. So all of these are they mean the exact same thing, they just sound different. You're using different words. So here our last one, we have our 0 point. We had 2 zeros, so now we need to add a third 0 before that 4. All right, so our next section here, we're going to be drawing some things. And my class are doing so well with this. I had students, all we did was just read this, and I had students popping out great conjectures. I'm going to go through this little step by step. We have LM equals 20, NM equals 6, and LN equals 14. So we're going back to segments, and we're talking about the lengths of the segments. So I'm going to draw it first before we make our conjecture. When we're looking at these, we notice that we have L and M in both the smaller ones, one or the other. And I had students saying, well, I noticed that if you add 6 and 14, you get 20. And that's exactly right. So we've got this segment, okay, with our endpoints, And the biggest segment out of these three is LM. So those are going to be our end points here, because they're all sharing these three letters. So we know these three letters are going to be collinear on the same line, or in this case, segment. We know from L to M is going to be 20. Now, we see this N that the other two smaller segments are sharing. So that means N is somewhere between L and M. I asked my students, is it in the middle? And some would say yes, some would say no. But then students start realizing that their lengths are different. And I had one student 7th period say, no, it's not in the middle because their lengths would be 10 each. And that's exactly right. So the point N is going to be closer to M end point because it's the smaller number. And not big deal. If you did it closer to L, no problem. But here's N. So NM is 6. LN is 14. So what we're noticing here is, like I said, if you add the two numbers together, you get 20. Well, that goes back to your part plus part equals whole. So we have part plus part equals whole. And this was our segment addition postulate. I'm just going to put post. Our next example here, I was asking my students, what are you noticing between the three names of these angles? And they noticed that each one of them shared that vertex A. The middle letter is A. We know that that is the vertex. So if we go over here and we can start drawing, we have a vertex A. We know that we're going to have three different angles that all share this. Well, to have a third angle in here, we're going to have to bring in another ray. So now we have, here's an angle, and then here's an angle, and some of you've probably already picked up on this. We look over here and we see that measurement of angle CAR. So CAR is the biggest measurement, so that's going to tell us that C and R are going to be on the outer rays, giving us this measurement is 57 degrees. And then we have that other letter E on the smaller two angles. So on this other ray, we're going to have ray A, E. And the measurement of angle CAE, as we're told, is 25 degrees. And the measurement of RAE is 32 degrees. So here, I had a really nice conjecture thrown out that I was not expecting. And it was all three angles share vertex A. And that is a conjecture. Yeah, they gave us more information that we can make another conjecture, but I really liked that. So we can say all share vertex A. And the other one, again, exact same thing as letter A, the A example right here. We have our part plus part equals the whole. So we have part plus part equals whole. This time we have our angle addition postulate. I'm going to abbreviate this. So we're still part plus part equals whole, but now we're doing the angles. Now this next one I want to talk through a little bit for a reason. Okay? We're going to start off with seeing that we have, it should have a triangle symbol in front of that ACE, because we're talking about a triangle. Okay, so we can draw a little triangle right there. Triangle ACE is a right triangle. So we are going to, or let's go ahead and finish. It's a right triangle with AC equal to CE. Just like polygons have vertices, the angles, they also have segments. So the segments are the sides of the polygons. So, because segment has a starting point and ending point, the two end points. You start somewhere, you end somewhere else. For example, if I draw this, okay, I'm going to start somewhere, and I'm going to end. There's a side of my triangle. So that's a segment, even though we don't have the actual points on there. So we're going to draw, and we're saying that these two sides, AC and CE, are going to be congruent. So let's go ahead and draw in our right triangle here. And we discuss, okay, what of these three letters, AC or E, goes with that 90-degree angle, the right angle. In a triangle, you'll learn in the next unit, it does not matter what order those letters go in. Absolutely not. Like with an angle, the middle letter has to be the vertex. Nothing with triangles. Take the three letters, put them in whatever order you want to. Okay? So a lot of students telling me C. One reason was because they saw C on both of these, and that's where those two sides are going to connect. But my question is then, why can't this vertex or angle up here be C, and this be AC and CE? And we walked through different things. I kept asking questions, and we came up with the conclusion that this is a right triangle, which means across from your right triangle is your hypotenuse. And a squared plus b squared equals c squared. Okay? We learned that the hypotenuse is always the longest angle or side, the largest side. So if that's diagonal line right here is the largest side, it cannot be congruent to the other two. So that means what we call the legs, the two that come together to form the 90-degree angle, that has to be C. And then where A is and where E is does not matter. And we know that AC measurement is the same as CE, meaning those sides are congruent. So a lot of us struggled with trying to figure out exactly what conjectures to draw here, but there are several of them. I'd have some students notice that, well, because we have this right triangle, angle C is a right angle, and that's a conjecture. So angle C is a right angle. We also notice that we have two congruent sides. A lot of students struggling remembering what kind of triangle has two congruent sides, and this is going to be your isosceles triangle. So we can put here angle ACE is an isosceles triangle. I also had a student that surprised me and told me that angle A and angle E are congruent. And it actually is absolutely correct, but we have not learned that yet. We will learn that in the next unit. Then on the isosceles triangle, you also have two congruent angles. Another conjecture could be that angles A and E are both acute angles, because they have to be, because you have a 90 right here. All right. So the last section that we need to, last section in topic we need to talk about, make sure we understand and we know, is what's called a counterexample. It goes along with these conjectures. What happens is we are going to, this actually has more stuff on here than your notes. I just now noticed I have an old copy. What we're going to, let me see how I can go through this. We're just going to write it in. I'm just going to write this in. Yours looks, I'm going to pause the video and go grab what yours looks like. So, and that was quick. I'm back already. This is what yours looks like. Our counterexample, when we have a conjecture, let's say that, I told you, hey, based on what I know, I'm looking outside and I can see the blue sky and there are no clouds. So my conjecture is it's sunny. Now, if I were to say I'm looking outside and there are no clouds in the sky, my conjecture is it is sunny. Well, I can prove that that's false. What happens at night when there are no clouds in the sky? It's not sunny. That's what we call a counterexample, that nighttime. This is going to prove a conjecture false. Prove that you're wrong. Okay? So, for example, the first one here, today is a weekend day. So you're given this information, and you're going to say, okay, well, if today is a weekend day, that means today is Saturday. Is that always true? Is every weekend day a Saturday? No. If it's not always true, you come up with a counterexample. And your counterexample here is just simply Sunday. That's a weekend day. In this case, you only have one counterexample. Sometimes you'll have more than one. Okay, the next one is, I'm going to give you the information, hey, I've got an angle here, it's acute. And then you're going to draw the conclusion or your conjecture and say, okay, it measures less than 90 degrees. Well, is that always true? Are acute angles always less than 90 degrees? Absolutely. That's the definition of it. Okay? So when your conjecture is correct, it is true, there are no counterexamples. So if it asks for you to put true or false, you put true. Here we'll just put there are no counterexamples. Right? We just put none. So I'm going to go to you on the next one. I'm going to say, hey, I'm thinking of a number, and that number is greater than 5. You're going to tell me your conjecture is, well, that number is greater than 7. Is that always true? No. What happens in between 5 and 7? There are a lot of numbers. If the number I was thinking of was 6, your conjecture is false. 6 is greater than 5, but it's not greater than 7. I mean, you could have 5.6. You could have 6.4. Okay, all of those numbers. The last one here, we're given this information. Hey guys, I got this polygon. It has 4 sides. And you're going to say, okay, well, if it has 4 sides, that polygon is a square. Are all 4-sided polygons squares? No. There are a lot out there. Okay? And the one that everybody's been telling me is rectangle. I also heard in class today, I heard rhombus, I heard trapezoid, parallelogram. They all have 4 sides, but they're not squares. So again, sometimes you have only one counterexample, sometimes you have multiple.